Salutations, Internet. Good time zone. I hope you're ready for a longer episode today because, as it turns out, I have a bit of a confession to make. In that, I believe it was 2 videos ago. No, I bet you it was longer than that. I said that the way to solve from time to eccentric anomaly angle would require graphical or numerical methods. That part is still true. However, I followed it up with, for the numerical methods, it is something that you don't really want to mess with too much. That part is not strictly true. It is still a pain in the butt, but it is not, it's not as big of a problem as I remember it being. See, a few days ago, I was trying to prepare myself for this, and I realized, oh, this isn't so bad. Especially if you're using the right method. So I think that is going to be our segue into the video. I have included just about all of the relevant equations for the time-position relationship. And we're going to be using a large chunk of them. We won't be using all of them, but we will be using a large chunk of them. So let's go ahead and jump over here. We start by marking this as an example. And we are going to be given a problem statement. You see, our dear SputNick, with whom we've become friends over the last several videos, has met with some amount of tragedy. Nope, too far. There we go. Has been met with some amount of tragedy. They've received a bit of an injury while doing their work in orbit. The injury itself is just preventing them from doing their job. That's kind of sad. However, we, being the good friends that we are, have a solution. We have a rocket prepared to go up and meet them. A good question for that is going to be, where do we meet them? Because while we do have parts for them, we need to make sure that they are able to receive those parts. Now, we're not going to mess around with matching speeds or anything. That's going to require some stuff that we'll get into for a later set of videos. But what we do need is to be able to intersect a point of their orbit at the same time as them. All right. So instinctively, reaching them at periaps might be a good idea. Just because it's the closest point to Earth. We can get there the fastest. Okay. Now, with our rocket, we know that, I say we know, we have been given that it will take a time of 30 minutes to go from Earth to periaps. From there, everything will sort itself out. So, what we need to find is, what position will SputNick be in at the time of launch? I will write it like this. At launch. At the time our rocket launches. What radius are they going to be at? What angle are they going to be at? In fact, let's go ahead and include that. What is their theta at launch? Okay. So from here, this problem statement allows us to, like I said, use most of the equations that we have derived for the time-position relationship. Most times we would need to convert from theta to E. We will then need actually going to need the average speed and mean anomaly equations. All of that will be fed into the Kepler's equation to find the time, or to find, since we will be given time, we will need that to find our eccentric anomaly at launch. And then in this example, we will need to convert back, but we don't strictly need to because we don't need to for all of it because we have an equation from eccentric anomaly angle to radius. So as you can see, we're going to be using most of these equations. Going back to this set, we're actually not going to be using those because we know that we are trying to meet at you know what? I'll explain when we get there. But right now, we know just about every characteristic of SputNick's orbit. We know what the semi-major axis is, which is 20,000, which is a good number to have, a good value to have on hand. And we also know the eccentricity, also a good number to have on hand. So now we can get to work. Numerical methods, plural. There's multiple methods that you can use to solve for this particular problem. The method that I'm going to be using is called Newton's method. Because among the ones that I have used, this one converges on a solution the fastest. So how are we going to use Newton's method? Well, we are actually going to want to use the mean anomaly equation here. So if I were to write that down, m is equal to E minus little e times the sine of big E. What we are going to want to do from here is turn this into a function. So we're actually going to move the mean anomaly itself over to the right side. E minus E sine of E minus M. And at first glance, at least while I was preparing to do this, I kept thinking that, well, what good does this do? This will always get us a value of 0. Not so, because as we move through the iterations, the M will stay the same while the E changes. And I'll, again, demonstrate what that means here in a little bit. But right now, you just need to know that this is our function, and it is not in terms of x, as I have written it here. It is in terms of E. The next thing that we are going to need for our Newton's method is going to be the derivative of the above equation. So the rate of change of E with respect to E is, unsurprisingly, 1 minus eccentricity, because it's a constant, times what is the sine of E. So the rate of change of sine of E is cosine of E. And because sine is negative, cosine is negative, our signs are right. Cosine of E. And then minus rate of change of M with respect to E. Like I said, M is constant. That becomes 0. And now we have the big things that we are going to need for Newton's equation, or Newton's method. So what is Newton's method? Well, if we're given an E1 value, to find E2, we will need to plug in the E1 value, and then we will need to subtract out of it the function of E over the derivative of the function of e. These are both e1s. And then you're going to do this with e2. So you're going to take your e2 and you're going to plug it into e1, or plug it into the equation that replaces e1, and that will get you your e3. You do this as long as you need to. To put this in a more generalized format, we'll have e sub k plus 1. The next iteration of our e is equal to e sub k minus f of e sub k over f prime of e sub k. And I'm going to go ahead and box that just so we don't lose it. It's not an equation that you can expect to see on the equation sheet, but it is definitely an equation that is worth holding on to. All right, you don't want to lose that. All right. So we have our functions and we have our method. The next question, what is our starting point? Where do we want our starting point to be? So I keep wanting to scroll down. I don't need to. There's a good starting point and there is a better starting point, at least in my notes. So the good starting point for E1 is going to be M. Nice and simple, right? If you determine what your M is, then you have a really good starting point for Newton's method. But a better one is M, as before, plus E times the sine of M. Oops. Sine of M plus E squared over 2 times the sine of 2M. So of the two of these, I'm going to do the first one because I need to find out what my M value is anyway. While this will get you closer to the value that you are looking for, as you can see, it is also more work to do. And I have enough work ahead of me right now that I don't feel like doing that right now, especially by hand. So let's do this. Let's find out what our M value is. And so this is going to be done. Oop, that was too much. Here, let's write this again. Let's find out what our M value is. So let's start at the time of intercept. Our mean anomaly at the time of intercept. So at intercept, that is our periapse, which we know to be defined as theta equals 0. When theta equals 0, so does E. So yeah, using this equation here, we will find what our M is. So that is going to be 0 minus 0.2 times the sine of 0. And it should surprise nobody that that value becomes 0. All right. So now we need the mean anomaly at the time of our launch, because this is the mean anomaly that we care about. This is going to be the value that we actually need to know. And that is going to be mean anomaly at the time of intercept. That was a weird looking eye. There we go. And then we are going to subtract out the average angular speed times the delta t. When you plug that in, We have 0 minus, we go over here, we see that n is equal to square root of mu over a cubed. Square root of mu, 3.986 is 10 to the 5th over a cubed, 20,000 cubed, and then our delta t. Scrolling back up here, we said that it takes about 30 minutes. We don't want it in minutes though, we want it in seconds. 1800 seconds. So we will come back down here. Times 1,800 to give us a mean anomaly at the time of launch of minus 0.401787257. And this is in radians. In fact, I will be using radians for just about everything during this video, because I don't want to try to convert between radians and degrees in the middle of the equation set, or in the middle of the method. I did that a few times and it was just a huge mess, so we're not going to do that. It's going to be radians all the way through until the end. Fantastic. So we have our mean anomaly, which, as we said, is also our starting value for E1. So, oh boy, for E2, I'm going to have to write extra small for this if I want it to stay in, if I don't want to take up more than one line. So we need E1, which is minus 0.40178727. We then subtract out the numerator. Numerator is F, where we have E minus E sine E minus M. So our E is E1 minus 0.401787257 minus E times the sine of E, so 0.2 sine of 0.401787257 minus M minus 0.40178727. And I did that in a different color because M is not E, but our starting E was M. This is where I kept tripping up every time I was running through the practice problems for this episode. I kept wanting to change my M along with my E's. Don't do that. And I got rid of that. Didn't mean to. All right. So now we can go to the denominator, which is going to be our F prime value. 1 minus E cosine E. Scrolling back down. 1 minus 0.2 times the cosine minus 0.401787257. And when you plug that in, you will be met with a value of minus 0.4976444791 radians. So that's not too bad. We had a change in the hundredths place, but we did objectively get closer to where we want to be. So now we need to do this whole thing again where we take our E2 value and we plug it into the equation to get us E3. Bear with me a moment. All right, so then you plug it into this equation here, again, keeping in mind that our M is still the same as before. It did not change. Doing that will give you an answer that is minus 0.497176,406. So already a huge improvement. Instead of changing the hundredths place, second decimal, we now had a change in the fourth decimal. All right, so now comes the real question. How many times do we want to do this? Ordinarily, you'll be given some arbitrary threshold, or you will define an arbitrary threshold for yourself. For me, I'm just going to go until I think the precision of my calculator is not going to give me any more useful changes, which is actually going to be once more. And I have the benefit of having variables on my calculator, so I just store this one. Hello? So I just stored that one into my calculator, and I'm going to have it spit out to me the next answer, which is going to be minus 0.497176,394. All right. Well, I'm going to step in here, not because I, strictly speaking, did anything wrong, but because I think it's healthy to do something, and this is a good opportunity for me to show it off. So my experience with numerical methods is passable, but minimal. It is healthy to make sure that if we're doing something new or doing something for the first time, that it does what we think it should do. And so I have made the claim that this value right here is the answer that we're looking for. But it does not appear as though I took the time to prove it. So I'm going to move over here. There's a little bit more space. And what we are going to do, let's hop over to the equation sheet. We want to make sure that when we plug in our value into this section here, that we get the time that we expect in this section over here. So let's plug that in and check. So our time is going to be equal to the square root of a cubed by mu. So 20,000 cubed over 3.986 times 10. Every time I do that, I start writing 10 times 10 to the 5th. Times, let's see, go back over here for it, times this value minus 0.497176,394 minus, let me double check, minus e times sine e. Ordinarily I wouldn't be jumping over to this page nearly as much, but I'm doing it because I don't have my notes handy. So 0 0.2 times sine. Curse my large handwriting. Of minus 0.497176.394 in radians. And so we should be expecting a time value of about minus 1800 seconds. And so we do get minus 1800 seconds. What we actually get is minus 1800.0000001 seconds. But this last digit right here is so far removed from this that we can kind of safely ignore it. And because I was curious, I also ran the numbers for our third value. Let me go ahead and do this and that. And, oh, sorry, not that. If you stopped one iteration sooner, you will also have minus 1800 seconds plus an additional 0.000045 seconds. So really that fourth iteration was not strictly necessary, but I think that has more to say about the power of Newton's method quickly converging on a result. So, and that's really what numerical methods is. You're just converging on a result instead of algebraically immediately finding a result. So now that we have confirmed that, yes, the value that we converged on does get us to 1800 seconds, we know that we used this method correctly, and we can continue onwards. And when you get changes all the way out to here, like that, and actually it's not even out there, is it? It's one more decimal over. When you start getting changes that small, it's not really worth continuing because you're talking about changes in inches or changes in centimeters over spans of kilometers. So it's really small at that point. At the same time, you can see why we want to have a computer do this for us, because it took us, 10 minutes to do all of this in here, whereas it would have taken a computer maybe 5/100ths of a second to do the same amount. The same amount of work. So now we have an E4 value. This will then be converted to theta. I will go ahead and convert that to theta. And again, you can use any of these equations that you want. I like my cosine equations, so that's the one I'm going to be using. E minus cosine E equals cosine E minus cosine of E 0.497176.394 over E cosine E minus 1. And 497176394 minus 1. Plugging that in gets you a value of 0.602830377, still in radians. Although at this point, we can convert back to degrees. Ooh, and I almost fell for that. I almost fell for one of the classic blunders. That's negative, because it's below the planet. And I'm using air quotes around that. It's below the eccentricity line. So that becomes minus 34.53963637 degrees. Which was actually one of the requirements that we needed. So we have it now. And finally, I'm gonna use the orbit equation for this one. And I like using a times 1 minus e for the numerator instead of h squared by mu. So I will use that. 20,000 times 1 minus e. 1 minus 0.2 squared over 1 plus 0.2 times the cosine of minus 34.53963637 degrees. And you will have 16,484.27. Oops, make that look neater. Kilometers. So I will box in both of these answers. All right. And I don't know how much of this video is going to get edited out, but it took me 32 minutes to go through all of this. And yeah, it's kind of a pain in the butt, but hey, you can do it. It's not that bad. All right, because of our efforts, today's video has a happy ending. So on behalf of SputNick, thank you for your help, and thank you ever so much for stopping by.